So having looked at the trends associated with the group 2 elements, the next little section on page 94 and the top of page 95 is about how they react. It will look like there's a lot of reactions to look at here or to learn off. To be honest, they're not the trickiest reactions you'll come across in A-level chemistry, and also a lot of them you will have covered in GCSE, so it should actually be in your head already. There's kind of 4 wee sections: reaction with oxygen, reaction with water, reaction with steam, and also reaction with dilute acids. And then we look at a couple of reactions of how the compounds react. The first reaction is reaction with oxygen, one you hopefully are quite familiar with. If you take any metal and react it with oxygen, you'll form a metal oxide. This example here, capital M, this represents any group 2 metal. So a swap and drop will give you just MO rather than MO2 or M2O. If we take a specific example, calcium with oxygen will make calcium oxide. So that same kind of trend will be true for every single group 2 metal. You could be asked for the observations for this. Essentially, it's just your flame colours because you are reacting these things in oxygen. Magnesium, calcium, strontium, barium, hopefully you remember from 1.10 qualitative tests. Magnesium has a bright white light you're quite familiar with. Calcium gives a brick red flame. Strontium a red flame. Barium a green flame. In all cases, you've got a white powder forming, and it's worth bringing in a general trend at this point. With any kind of group 2 compound, and this is true for the rest of this topic, whether it's an oxide, a hydroxide, carbonate, whatever, observation-wise, group 2 compounds are generally, if they're solid, they're white solids. And if you dissolve them in water, if they are soluble, they'll form colourless solutions. They're quite kind of mundane in terms of their appearance compared to things like transitional compounds. They generally will be colourless solutions or white solids. Next one is the reactions with water. Again, something you did do in 5th year with your reactivity series. If you take any metal and react it with cold water, you'll form a metal hydroxide and some hydrogen. So here's an example of strontium. Strontium plus 2H2O goes to strontium hydroxide plus hydrogen. Observation-wise, there's a wee bit more going on. With all of them, you are going to get bubbles being produced. Looking at the equation, it's clear where they're coming from. It's because you're making hydrogen that will make bubbles. Remembering back to your trend reactivity, as you go down the group, you will get a bit more reactive. Magnesium near the top is very unreactive in comparison. You'll just form the odd bubble and the soluble dull. However, when you got down to calcium, strontium, barium, they're a bit more reactive, so you get a lot more heat released, and eventually your metal will fully disappear and react, whereas with magnesium, it'll just sort of sit there. It's not going to disappear. Calcium is the one that stands out as being a wee bit unusual. There's quite a few observations for it. When you chuck a piece of calcium into some cold water, the first thing it'll do is it'll sink, because it's quite a dense metal. However, once it starts reacting for a wee bit, it will eventually rise up. It's going to rise up to the top because it starts producing hydrogen at such a rate it actually propels it up like a wee jetpack to the top. So the rising part of that is due to hydrogen production. The appearance of the solution at the end. So we talked about the fact that group 2 compounds should be colourless solutions when they dissolve. There's a slight snag with the product of this reaction. Calcium hydroxide is not particularly soluble. It's not completely insoluble either, so it's not a precipitate, but we would call it a slightly insoluble solution. So we get a cloudy white solution is what that looks like appearance-wise. You could be asked to draw a diagram for this one for how you would react a group 2 metal with water. They're not very reactive, so it's not a very unsafe way to do it. You can just trap it underneath the funnel and put a boiling tube on top upturned with water inside it. Why you might do it like this is essentially just to trap any hydrogen gas if you wanted to test it to prove it was hydrogen. So that boiling tube on top allows you to trap hydrogen. Third type of reaction with steam. Again, another part of reactivity series last year. This one's a little bit strange because it goes against your chemical common sense. When you're reacting a metal with steam, you are still obviously reacting with H2O, and everything you know about chemistry relies on the fact that it's quite reliable that 2 compounds, 2 substances together, will always react in the same way. This breaks down for this case. Metal with cold water gave you metal hydroxide plus hydrogen, but suddenly metal with hot water, essentially steam, gives you metal oxide plus hydrogen. it looks kind of incorrect. It's not actually incorrect because in this particular case, you've actually got two reactions going on simultaneously, which I try to explain. When you do react, we'll take magnesium and react it with steam. What you should get is magnesium hydroxide, because that's what happens with cold water, and that actually is what happens with steam. You get the same reaction that you do with cold water. However, the problem with reacting these with steam, why you get this slightly different equation is it's with the metal hydroxide. Metal hydroxides in general aren't particularly stable at high temperatures. If you're reacting your metal with steam, it is going to be at a high temperature, so the metal hydroxide can't actually stick around that much. It will decompose due to heat and immediately break down into the metal oxide, in this case magnesium oxide, plus hydrogen. So this simple looking equation actually becomes a bit of a mess because you got a first reaction, then a second side reaction as your product decomposes. If you actually do a wee bit of analysis of what that is as a whole equation, if I write out down here, so if I take magnesium and water, so first of all I form magnesium hydroxide, but it's all used up or all converted into magnesium oxide, plus, that should be water here, magnesium oxide plus water. And we still got this hydrogen from the first reaction. If you look at what we got now, you've got water on both sides, but actually you can cancel down a wee bit. So it becomes magnesium plus H2O goes to MgO plus H2, which is the equation you've got in your notes there. So it looks like it's wrong because it's a different reaction for the same substances, but with a wee bit of analysis, it's due to a second reaction taking place. Your hydroxide decomposing gives you the metal oxide plus hydrogen. Observation-wise, nothing too groundbreaking here. Your observations are essentially the same, like a wee comparison to your metal reacting with oxygen, because in this reaction you're eventually forming a metal oxide, so you'll kind of get the same observations that you got up here when you made the metal oxide. You generally get a flame colour, so magnesium gets a bright white light, calcium red flame, barium green flame, and you will get that white powder formed because you are forming that metal oxide, which you've looked at before. The diagram here is a little bit more complicated. Again, you should recognise it from last year. A couple of wee points to bring up. Just the presence of the damp mineral wool. Obviously in this reaction you need steam. Steam requires you to heat water up. So you soak some mineral wool. Mineral wool is like cotton wool but it's heat resistant. So it's not going to go on flames. If you heat it up, you're going to make steam. And if you notice that the diagram here, you've got arrows in two places. You need to both heat the wool to get it hot enough to make steam. You also need to heat the metal, get it hot enough to overcome the activation energy to react in the first place. So you do actually have heat in two places, and that's an important part of it. Right hand side is just a way of collecting the hydrogen gas you expect to make. Again, be really careful if you ask to draw this. Remember that the tube has to be completely open the whole way down. It can't be going through a closed bung. Make sure it doesn't go through the trough. Behave shelf and gas jar on top of it. Make sure the gas jar is filled up with water partially, because that's how you collect the gas. Make sure the water level in the trough is above the beehive shelf, otherwise the gas will just escape out and not go into the gas jar. Final type of reaction is another reaction you did probably more in 4th year with acids than 5th year with reactivity series. These group 2 metals, like most metals, will react with an acid to make a salt plus water. Metal plus acid goes to salt plus water. Couple examples: a metal with hydrochloric acid will make a metal chloride plus hydrogen. And at this point I just realised there's a horrible typo in these notes, apologies for that. As you probably were screaming at your screen, they don't make a salt plus water, it should be a salt plus hydrogen. Apologies for that. So metal plus hydrochloric acid will make a metal chloride plus hydrogen. A metal plus sulfuric acid will make a metal sulfate plus hydrogen there. Observation-wise, heat is released, it's quite exothermic. Bubbles are produced because you're making hydrogen. The metal will eventually disappear. It's not there at the end of the reaction. It's turned into the salt form, which can dissolve. The colourless solution will form, again, metal compounds, if they dissolve them water, tend to be colourless in solution, group 2 metal compounds, that is. The final type of reaction to look at, final category, is a little bit different. It's about your compounds and how they react in group 2 compounds. So the one we look at is the group 2 oxides. So if you think about where they could have come from, you can make a group 2 oxide from 2 different methods. You can react a metal with oxygen to make a metal oxide. Or as we looked in the previous page, you could react a metal with steam, which will give you metal oxide as well. Either way, you can take that metal oxide and react it further. So with those metal oxides, you may or may not remember back and forth here with acids and alkalis, you had a category of compound called a base. Bases are things that neutralise acids. What you might remember from that as well is that generally that bases tend to be metal hydroxides or metal oxides. Metal oxides are actually a base or a thing that will neutralise an acid. A slightly fancier way of writing that at AS level, it's a proton acceptor. Protons are what we refer to as H plus ions, which obviously are being made by acids. So if you take group 2 oxide and react it with water, it will still act like a proton acceptor. So MO, a metal oxide, plus water will make metal hydroxide. So calcium oxide plus water makes calcium hydroxide. It can be a wee bit tricky kind of understand what's going on there. So I'm going to actually draw this out a little bit differently. I'm going to sketch out all the individual atoms in this equation. So metal oxide is this a metal 2 plus ion if it's in group 2, and it's got an ionic attraction to an oxide ion. You're reacting with H2O. And if we look at what we've got on the other side, we've still got that metal 2 plus ion because it's a group 2 metal. It's now bonded to 2 hydroxide ions. So what basically has happened here is that this oxide ion in this case has stolen an H plus away from the water. So in other words, it's acted like a proton acceptor, an H plus acceptor, leaving with this being OH, because it's taken an H plus, and that also gives you a second OH minus left over once the H plus has been removed. It gives you 2 OH minus ions, which both join to your metal ion, giving you the metal hydroxide. So that is a case of your group 2 oxide acting like an H plus or proton acceptor, basically a base. They also react with acids, which is probably one you're more familiar with. You've got the trends here. So metal oxide plus hydrochloric acid makes the salt plus water, the chloride plus water. Sulfuric acid makes a sulfate plus water. Nitric acid makes a nitrate plus water. Again, just to analyse that one to show you, it is actually acting like a proton or H plus acceptor. If we take the top one here, we take a metal oxide again, so 2 plus, an oxide with 2 minus. If we take HCl, this equation is 2HCl. So there's 2 H plus Cl minuses. Remember, acids tend to split up in water or ionize. What this oxide ion is going to do here is take both of those H pluses to form water. The Cl minuses from the acid are left over and will join to the metal ion. So what you end up with this. So M2 plus is joining to Cl minus twice. And the byproduct is a molecule of water. So again, your base, your metal oxide, is acted like an H plus acceptor, taking the H pluses from acids to leave a salt plus water left over at the end. Observation wise, heat released, exothermic, solid disappears because you're using up your base, and the colour solution form because that's just a salt plus water, which again is just a group 2 compound, which tend to be colourless.